Hi, I wanted to introduce you to the third module. In this module, we'll start taking some ideas that we've been using in previous sections, and we're going to combine them together. And the improper integral is one of those tools that really unifies and shows up all over the place in mathematics, but especially it's a really unifying theme of this course. So some of those class applications to start out with are the fact that improper integrals always end up involving limits. And very frequently those limits end up having indeterminate forms in them. So we end up applying L'Hopital's rule. But also we can use improper integrals as ways to make sense of things that come from polar and parametric coordinates. So we could take some sort of parametrically defined curve and look at the way it moves in the plane and maybe try to determine whether or not if we let t go to infinity, would that overall arc length be finite? An example where that might happen is, say we had a curve where the way that the argument t was showing up, the speed, if you will, at which the curve is traversing distance could be shrinking exponentially. Like what if x and y were both functions really of like e to the negative t, then as t goes to infinity, those x and y curves are moving smaller and smaller distances because e to the negative t heads to 0 as time goes to infinity. But there are also just some classic paradoxes where this shows up, and one of them is the example of what's called Gabriel's horn. So Gabriel is, in the Christian tradition, the angel who's supposed to ring the horn at the moment of judgment, and so if you will, this is supposed to be this moment at which the finite meets the infinite, if you will. And the example of Gabriel's horn takes a class of curve, 1 over x, and you rotate it around the x-axis, and then you consider what's left, that volume of revolution. If you've gone all the way out to infinity, you consider that as if it were a horn. And what's interesting is it turns out there has to be a finite volume that you could fit inside of it if you thought of it as a solid of revolution, but the outer surface ends up being infinite. I've included a really short little animated video I found that probably a couple calculus students at a high school made that just shows you how those computations run because they're kind of simple, and it's got neat animation. To sort of examine this phenomenon. What if you had a horn that you know has finite volume, but it has infinite surface area? So if you wanted to paint it, it would take an infinite amount of time to cover the whole thing with paint, but you could paint the inside if you had this finite amount of paint, could pour it on the inside and allow it all kind of stick to the edges, as long as you could get an infinitely thin layer to have that happen. So the thickness of the paint would kind of get in the way. You'd still end up having the paint sort of not be able to do its job for that reason. It's a really cool example of what happens when you try to take something infinitely long and then force it to sort of live in the real world. So other places that improper integrals will come up in the future are in our work with series. We'll have an interrelationship between improper integrals as these infinite, right, like integrals are sums of infinitely many little rectangles, and now we're going to take them and do that summing out to infinity. An infinite series will be sums of an infinite sequence of numbers. So there's a cool relationship about how those things can connect and how you can use one to get to the other. Additionally, improper integrals show up in integral transforms, and the basic example that most math majors and minors see is the Laplace transform, which is a technique used in differential equations, and you'll see it in physics like electricity and magnetism classes and in some engineering classes. So welcome to Module 3.